once again, Adam Eldridge, West Valley High School of Yakima, teaching in the Central Cornerstone program. And today we're going to look at Section 7.2 in Central's pre-calc book. And we're going to talk a little bit about calculating arc length, calculating areas of sectors and segments, and calculating linear and angular speeds. To start with today, I want to look a little bit at deriving an arc length formula for circumference. From circumference. So let's start with a circle. And I need to get on my pen here. We'll start with a circle. And we'll start with a circle of radius r. And for ease of discussion here, since I can't have some back and forth with you, I'm going to set an angle here at 120 degrees. Now yes, we just spent some time talking about radian measure, and we're going to come back to that today, but I want to start with what we're probably more comfortable with, and that's a degree measure. So I've started with a circle, radius r, and a central angle of 120 degrees. We know from previous discussions that the arc length we're looking at is right here. Now, arc length directly corresponds with the circumference of the circle. So let's go back into our days of geometry and be reminded that the circumference of a circle is equal to 2 pi times r. Now, for this particular problem, I want to find that arc. And that arc represents a portion of my whole circle. So if the whole circle is 2 pi r, and this sector of my circle is 120 degrees, well, that's 120 degrees corresponds to 1/3 of my entire circle. So my arc length should be 1/3 my arc length for this particular problem should be 1/3 of the circumference, which we could rewrite as 2/3 pi times the radius. Now let's look at that 2 pi over 3, and is there a connection between 2 pi over 3 and 120 degrees? And I'll remind you from our previous discussion that 120 degrees, if I want to convert that into radians, I would take 120 times pi over 180. And I see that 120 degrees is equivalent to 2 pi over 3. So the 2 pi over 3 is actually corresponding to that central angle in radian measure, and I notice that this is essentially equivalent of the arc length is equal to the central angle times the radius. Well, that's not an entirely new concept, because when we defined radian measure, we defined radian measure of a central angle to be the length of the arc divided by its radius. And if we multiply both sides by the radius, we see that S is equal to R times theta. Now this is the formula for when you are in radians. We can use this formula when theta is expressed in radians. So we have a couple options. If we are given an angle, a central angle in degrees, we can either convert it to radians and then take that angle times the radius, or we can do what we started with today, which is to take the part of the circle that we're dealing with, in this case 1/3, which we achieved by taking the 120 degrees divided by the whole circle, which is 360. So formula for arc length is S is equal to R times theta. The other day we represented that in a different form, and if we wanted to calculate the radius given the central angle and the arc length, we could do that as well. Radius would be equal to the arc length over the central angle in radians. So that's a little bit about arc length. And if you're sitting there on an exam and you get stuck, think back to what you know you know about circumference, and arc length and circumference have a very direct relationship. Now we want to look at deriving areas of sectors from the area of a circle. So again, we're going to start with a circle with radius of r, and I'm going to create a sector here. So that's an r right there, an r right there. And we want to find the area. We want to find the area of that particular sector. Earlier, we discussed how to find the arc length, and now we're going to talk about the area. Now let's go back to what we know about areas. We know the area of a circle is pi times the radius squared. And let's say that our sector had a central angle of 60 degrees. Well, the area of my sector then would be 1/6 of the entire area of the circle. Where I got the 1/6 was if I took my 60 degrees divided by 360 degrees, I get 106. The 360 again represents the entire circle, and I'm only looking at a part of it. So the area of this particular set would be 1/6 pi r squared. And let's look for relationships now between the 60 degrees, that angle in degrees, and the angle in a radian measure. 60 degrees in radians, we're looking at pi over 180, would be a pi over 3 radians. And in my answer here, I see a pi over 6 times r squared. And if I look back at my original area formula, I have an area is equal to pi times r squared. Well, that pi, compared to when we're talking about angles, we know that a full circle is 2 pi. So if I substituted in here, the area of a sector could be equivalent to 1/2 whatever our central angle is times the r squared. Now again, the reason for the 1/2 is when I want a whole circle, the whole circle would have a central angle of 2 pi. And I know from my earlier discussions in geometry that the area is pi r squared. So how do I get a pi when I start with a 2 pi? Well, if I input a 2 pi in for my theta and multiply it by 1/2, that would yield the pi that I'm looking for in my area formula. So we've got an area. Again, this formula for area is the area of a sector where your central angle is in radians. If you're given an angle in degrees, again, you can use a ratio of how much of the sector is compared to the whole circle, and we can compute it similarly. So again, I want to remind you to go back to what you already know. You know the area of a circle. A sector is just a portion of that circle. You know the arc length corresponds to circumference, so take what you know about circumference and relate it to arc length as well. Now, the next topic is calculating the area of a segment. And a segment of a circle is the region bounded by an arc of the circle and its chord. So to define what that segment looks like, we take the chord of the circle, located there. Here is our radius, here is our arc, here is our central angle. The segment is this area that is bounded by the chord and the arc. So we're going to look at how can we calculate this area right here. Well, let's take a moment and think about how these two concepts relate to what we already know. Here is a triangle. Different color. pen here. Here is a triangle. If we were to take the area of the sector and subtract the area of the triangle, then that would yield the area of the segment. So again, all pieces you're familiar with. You know how to find the area of the sector, you know how to find the area of the triangle, you know how to subtract. Those are the computations we are going to use in order to calculate the area of a segment. A couple of reminders. Again, from the last slide, we saw that the area of the sector, so area of the sector was 1/2 the central angle in radians times r squared. We know area of triangle is 1/2 base times height, but in a problem like this, we can go back to what we learned previously in chapter 6, that an area of a triangle is also equal to 1/2 the product of these two sides, which are both r in this case. I'll write them out separately. It's 1/2 AB times the sine of theta. And if you go back to early in chapter 6, you'll see where we developed that formula. So let's look at an example. Finding the area of this segment, let's say that we start with a radius of 4, and we are going to start with a central angle of pi over 7. So take a few moments and try to calculate the area of the sector, which is this area that is shaded in blue. So we are going to take the area of the sector, which the area of the sector is 1/2 times our central angle, pi over 7, times the radius squared. So that's the area of that entire sector. And we are going to subtract the area of the triangle, which is 1/2 4 times 4, which is 4 squared, times the sine of pi over 7. And let's put centimeters on this. Let's go units. I didn't do that on an earlier example. So these units are in centimeters squared and centimeters squared. When I calculate this out, I get 8 pi over 7 for the area of my sector, minus 8 times the sine of pi over 7. And my units on this is going to be centimeters squared. And let's go to our calculator. Again, from earlier discussion, we should be in radian mode. And I want to clear what I have in here previously. So I wanted to take our 8 pi divided by 7. And I want to subtract our 8 times the sine of pi over 7. So again, the first part there, the 8 pi over 7, is the area of the sector, and then we're subtracting the area of the triangle, and this will get us the area of the segment. So let's look at one final concept today, and that's the idea of angular versus linear speed. And when we talk about how fast something is turning, we need to be sure that we're communicating what type of speed it is that we're looking at. So I'm looking at angular versus linear speed here. Angular speed is measured in units like revolutions per minute or radians per second. If you think about it, if you think about a record, which, or in your case, a CD. It used to be we would teach this with record players, but now we no longer talk about that. Let's say that we're talking about a CD or a DVD, a disc that's turning. We can define how fast that's turning in a revolutions per minute type of situation. So, I don't know, an old record might be at 33 revolutions per minute. That means that that disc is making 33 complete revolutions in the span of 1 minute. Well, if we take the radial axis here, centered here, and we took this axis and we're rotating it, it's rotating at a speed of 33 complete revolutions per minute. But each one of those revolutions is going through an angle of 2 pi radians. So each one of our revolutions, one revolution is 2 pi radians. So if I knew something was spinning at a rate of 33 revolutions per minute, or RPMs, I can convert that to radians per minute, or radians per second, or radians per any unit of time that I wanted. I would take that 33 revolutions per minute, and I know that one revolution, it's kind of like going back to chemistry class, doing a little dimensional analysis. One revolution is equivalent to 2 pi radians. So I'm looking at 66 pi radians per minute. And that's talking about how quickly the angle is moving. Linear speed is a distance. So if we're talking linear speed, we're actually charting, let's say we had a point on the edge of our CD or on the edge of our record. This point is turning. Okay? And if we're talking about linear speed, we're looking at a distance over time. Now, if a point is on the edge here, that sounds a lot like the distance being traveled is related to the circumference. So similarly, if I started out with 33 revolutions per minute, and I wanted to find out how many inches per second, let's say we had something that had a radius of 6 inches on it, I could convert that into inches per minute, or inches per hour, or inches per second, or miles per hour by doing some conversions. So let's say that I want to get this in terms of inches per second. So 33 revolutions per minute, this is an example of an angular speed, and we can convert that into a linear speed. I know that one revolution is 2 pi radians. It's also equivalent in this particular case to the circumference, which would be 2 pi times 6, which would be 12 pi inches. So in this case, and I want to look at taking 33 revolutions per minute. One revolution goes downstairs. I'm looking at 12 pi inches. So at this point, I would have inches per minute. And then if I want to convert minutes to seconds, I know that 1 minute is the same as 60 seconds. So my minutes will cancel, revolutions canceled, and I now have inches per second. But I want to take us right back up here. Circumference has this 2 pi as a part of it, 2 pi times the radius. And I know that radians here, I have 2 pi radians per revolution. It looks like if I just take my angular speed and multiply it by the radius, I will get the linear speed over the same equivalent unit of time. So what I mean by that is if we stopped right here with inches per minute, that's the same as if I would have taken the radius times my angular speed. So the linear speed here, with the same unit of time, is the same as my angular speed times the radius that I'm turning. And it kind of goes back again. If we look at when we're doing angular speed, we said 1 revolution was 2 pi radians. When we're doing linear speed, we said 1 revolution was 2 pi times the radius, so that the angular speed is going to be the radius times bigger than the angular speed, provided you're looking at the same unit of time. If I'm comparing an angular speed with per minute and a linear per second, then I'm going to have to do a conversion as well to get that time difference. So let's look at one last example here. A wheel has a diameter of 36 inches and turns at a rate of 37 revolutions per minute. Find the angular speed of the wheel in radians per second, and also find the linear speed of a point on the circumference of the wheel in feet per second. In feet per second. So let's start with angular speed, 37 revolutions per minute. And my goal here is to get in radians per second. So I know that 1 revolution is 2 pi radians. I know that their 1 minute is 60 seconds. So my minutes cancel, my revolutions cancel. My units that I'm left with are radians per second. And then it's 74 pi radians per second. If I want to find the linear speed, again, I can start with 37 revolutions per minute. I know that 1 revolution is equivalent to the circumference. And my diameter here is 36 inches diameter. So that means that my circumference is 36 inches times pi. The circumference is also pi times diameter, equivalent to 2 pi r. So I want it in feet, so I'm going to go ahead and do a conversion here. I'm assuming you all can stay with me if I go that my diameter here is 3 feet, which makes the radius 1.5 feet. So 1 revolution is equivalent to 1 circumference on the edge. So my circumference is 3 feet, and I want to go per second. Excuse me, 3 pi. Don't forget about that pi. Circumference is pi times diameter. And I want to go 1 minute per 60 seconds. Which, when I look at this value, it's 111 pi over 60. I forgot that 60 up there. Please make a note in your notes that it's 74 pi radians over 60 seconds, and this would be feet per second, which I will notice that if I'm looking at the linear speed in seconds compared to the angular speed in seconds, if I took that angular speed in seconds, 74 pi over 60, and multiplied it by our radius is 3/2, then that is equivalent to my linear speed. So another way of getting linear speed would have been to take our angular speed times the radius. Radius in this case was 3/2 feet, and those are, in fact, this is equivalent to this. So a couple different approaches to finding linear speed and angular speed. I like to equate it back to what you already know. You've done dimensional analysis in previous math and science courses. It still applies here. The key is to set up your conversion factors in such a way that the units will cancel and you end up with the units that you desire. And that concludes section 7.2.